So I think the hardest thing about this unit has been finding the area of polar curves and specifically the limits of integration. So what I've done is made a table of the 6 types of questions that Miss Patel could ask us tomorrow on the test, because there's only 6 of them. So I thought I would outline them and how to find the limits of integration for each of them. So the first type of question is if she says find the area of the region bounded by the graph of a polar curve, and she says all of it or the interior, and in that case the limits of integration are 0 to 2 pi. Um, and there's no, like, it's nothing, if she says nothing else about it, then she wants you to use 0 to 2 pi because that's going to be one full rotation of the entire polar graph. And so this will work for any polar graph. The second type of question she could ask is the area of one petal, which requires that you use 2 consecutive zeros as your limits of integration. So if you have like this sine graph petals and she wants just this, you would find the zeros of the sine graph and then use 2 consecutive zeros to find as your limits of integration. This third type of question she could ask you is what's the area of the inner loop? The inner loop, if you don't remember, it's a function that has an inner loop like this. She wants just this area. You would find the 2 consecutive zeros, and those would be your limits of integration. So up to here, it's pretty easy. And then we get to the last 3, which are kind of more complex. So the fourth type of question that she could ask you is the inside-outside, which I think of big R, small r, inside-outside. So what you would do is use the washer method. You would sweep the area from the origin, and the first function that you touch, or the closer function, is the small r, and the further function is the big R. So it's kind of like the washer method. And then you would square both of them. And then the fifth kind is the area common to 2 functions, or the common interior. So both of these have to deal with 2 different functions. And the rest of them only have to do with 1. So the area bounded by the graph of 1 function, area of 1 petal of 1 function, area of the inner loop of 1 function, but these 2 have to deal with 2 functions. So if she says she wants the area common to 2 functions or the common interior, then you would use the majority function's area plus the area of the sliver, which we'll talk about later. And then the last kind of question that she could ask you is the area between the loops of something. So, and this again has to deal with 1 function, and that would be something like if who has an inner loop, she wants everything except for the inner loop, which is the area between the loops. And so for that one, you would find where you first visit the pole and then subtract the region from the 2 consecutive zeros from that. So it's kind of tough when you say it in words, but I think once I do an example, you'll understand it better. So just a couple of things before I start. In all cases, the area is 1/2 of the integration from a to b of r squared d theta. And when I talk about sweeping from the pole, or just the pole in general, that's where r is equal to 0, which is at the origin, so it's right here. It doesn't mean where theta is 0, because theta could be 0 out here where r is equal to 4. But if you're here, it doesn't matter what theta is because the radius is always going to be 0. So the pole is the origin. So number 1, it just says find the area of the interior of this function without any specifics. Like, it doesn't say find the area of 1 petal or anything. So in this case, since going back to our chart, it only wants the area of the interior, the limits of integration would be 0 to 2 pi. So I don't even have to sketch a graph or set the function equal to 0 because I know that my limits of integration are going to be 0 to 2 pi. And I can just plug and chug into my formula. For number 2, you have to do some more work because it's asking for 1 petal. And when it says 1 petal, you know that it needs 2 consecutive zeros. So I'm going to actually find the zeros before I think about consecutive zeros by setting r equal to 0. So we get sine of 3 theta equal to 0, so that means that 3 theta is equal to 0, pi, and then we have to add 2 pi to both of them, and then do it again because it's 3 theta, and then divide everything by 3. So here we get theta is equal to 0 divided by 3 is 0, pi over 3, 2 pi over 3. 3 pi over 3, which is 5, 4 pi over 3, and 5 pi over 3. But I really didn't need to do that because all I needed to do was select 2 consecutive zeros as my limits of integration. So I could do 0 and pi over 3, or pi over 3 and 2 pi over 3. Like, it doesn't matter which 2 you do. So I'll do 1/2 the integration from 0 to pi over 3 of 2 sine 3 theta squared d theta. Or I could do from pi over 3 to 2 pi over 3, or pi to 4 pi. Like, it doesn't matter which two as long as they're next to each other. And for number 3, it says find the area of the inner loop. So inner loop also requires 2 consecutive zeros. So I'm going to find the zeros. And then, so cosine theta is equal to negative 1/2, and then theta is equal to 2 pi over 3 and 4 pi over 3. So these are my zeros, and in this case, they're the only zeros, and so they're consecutive. But if you ever get anything where it's like more than 2 zeros, then you would do any 2 consecutive ones, and you'll never get a situation where it's only 1 0 when it's asking you to find the inner loop of something. So you just choose 2 consecutive zeros. In this case, the 2 consecutive zeros are the only zeros, but normally you would just choose 2 consecutive zeros and then plug and chug into the equation, and then use your calculator to evaluate this. So I'll do this equation in the next example.